Okay, so this problem is going to be a little more intricate than you're going to see exactly like on a test, at least the first part, and I'll explain why. We want to find an algebraic equation that the eigenvalues satisfy, but notice I haven't told you whether or not the eigenvalues are positive or negative. So this is going to be very similar to problem 5 from homework 9. Remember on problem 5 from homework 9? Remember on problem 9 from homework 5? 5, yeah. I said something like assume the eigenvalues are positive. Now we're not exactly going to have that here. But again, on the test, it's not going to be as intricate as this problem is going to get. Okay, so I'm going to start here. I'm going to rearrange the equation. We're going to get phi double prime is equal to minus 9 plus, oh, let me do lambda plus 9, lambda plus 9 phi prime, and then we're going to have the boundary conditions with the given. Now, if we had just Dirichlet or Neumann boundary conditions, we would know how to handle this. We would say, okay, the square root of lambda, we would say, okay, the square root of lambda plus 9 has to be equal to a positive number. It has to be equal to k times pi or k pi plus pi over 2, something like that. But now, with this different boundary condition, I don't know, maybe it's no longer clear that maybe with this different boundary condition, maybe it's no longer clear, excuse me, that we're going to have positive eigenvalues. Okay, so let's because it's important for right now. It's important what lambda plus 9 is. I'm going to call that gamma. Okay, let's write this as, so gamma equals lambda plus 9. And I want to show something about gamma. I want to show basically that gamma has to be non-negative. Now that's not going to mean lambda has to be non-negative. It's going to mean lambda plus 9 has to be non-negative. Okay, so we want to show that gamma is greater than 0. So we want to show that gamma is greater than 0. Okay, so how can we do this? So there's two ways. One way is to say, okay, well, what if gamma is negative? Then minus gamma is positive, and so the general solution is going to be a linear combination of exponential functions, like e to the square root of minus gamma x, plus be to the square root of gamma, the square root of minus gamma x, just typical second order differential equations there. The characteristic polynomial would be r squared is equal to minus gamma, but gamma's negative, so that'd be r squared is equal to the absolute value of gamma. Okay, and then make some arguments to show that this means that that the eigenvalue that gamma has to be positive. Okay, that's one way to do it. I'm going to do it a slightly different way. And I'm going to do it in a different way that's going to be related to how we do it down here. Okay, so let's do that. So we want to show that gamma is greater than 0. Okay, so what can we do now? If phi double prime is equal to minus gamma phi and satisfies the boundary conditions, then we're going to have the following. So we're going to look at the integral from 0 to 1 of phi squared. Okay, now phi is equal to minus 1 over gamma times the integral 0 to 1 phi double prime times phi. And now we're going to do integration by parts. Okay, so we're going to have the integral, we'll have the boundary terms. So phi prime, phi prime. I mean, essentially what I'm getting here is the Rayleigh quotient for this problem, for this problem here. Okay, so we're going to have this, and then minus the integral from 0 to 1, putting the derivative from the double derivative onto the no derivative, and we get that. And then what are we going to have? We're going to have minus 1 over gamma. I'm just going to distribute this. And then we're going to have plus 1 over gamma times the integral, because the minus signs are going to cancel. So we're going to have this times that. Let's look at that now. What did I do wrong? I always do that. Lambda. Okay. Whoops. Okay, that's what we have. Using the boundary conditions. Actually, I'm just going to keep this going. Okay, the boundary conditions. Let's think about what's going to happen with the boundary conditions. Well, phi of 0 is 0, so the only boundary condition we have that's not 0 is when it is for 1, and so this is going to be minus 1 over gamma, and then it's going to be phi prime of 1, phi of 1, and then plus this, plus the integral. Okay, and now we're going to use the fact that, okay, we know that phi prime of 1 minus phi of 1 is equal to 0. So in other words, phi of 1 is equal to phi prime of 1. So this is now minus 1 over gamma, and I'm going to write this as phi prime of 1 squared, and then plus this. Okay. So now what I want to do here, and actually, see, I probably needed to have the gamma on the outside. I probably needed to keep the gamma on the outside. I think I'm going to go back and fix that, but I'm not going to record that. Okay, so this is what we have here, and what I want to do, I've got a minus sign here. What I'm going to do next is I'm going to show that this quantity right here is negative. I'm going to show I'm going to show it's not positive. Maybe it's equal to 0. Show it's non-positive, and then minus that is going to be positive. Okay, so now, this is going to use something that maybe a lot of you haven't seen before, at least a few things, some ideas maybe as well. By the fundamental theorem of calculus, so we know phi of 0 is equal to 0, so then phi of 1 is going to be equal to the integral. So it's phi of 1 minus phi of 0 is going to be equal to the integral from 0 to 1 of phi prime. That's the fundamental theorem of calculus. I should have minus phi prime of 0 here, but that's equal to 0. So let me just do it like this. Phi prime of 1 is equal to phi prime of 1 minus phi prime of 0, since phi of 1 is equal to phi of 1 minus phi of 0, since phi of 0 is equal to 0, so that's equal to that. Okay, now we're going to use something called the Cauchy-Schwarz inequality. And basically, or you could either think about this as an application of Cauchy-Schwarz inequality or Jensen's inequality. So now by FTC and the Cauchy-Schwarz inequality, or the Jensen's inequality, we can write the following. We can make the following estimate. This integral here this integral here is going to be less than or equal to the square root of this. If you're not familiar with what that is, look it up. You don't have to use Cauchy-Schwarz inequality if you do the thing where you assume that gamma is negative and look at the exponential function. That way you don't have to do this. Okay, but this is one thing to do. Okay, so what do we have here? So if we just run this, yeah, this is less than or equal to that. If we square both sides, so another thing that we need to do here is the following. So if we assume that phi of 1 is greater than or equal to 0, which we can do since if it isn't, we apply this argument to minus phi of 1. Okay, because notice that any multiple, all we're assuming right here, all we're assuming right here is that phi double prime satisfies this equation. If phi of 1 is equal to, if phi of 1 is negative, we can multiply both sides of this by minus 1. The equality is still true, and now phi of 1 is going to be positive. Okay, so we can always make that, and the boundary values are also going to be true, right? If you multiply phi by minus 1, well, phi of 0 minus phi of 0 is still going to be 0. If you multiply this by minus 1, that's still going to be 0. Okay, this is just the basic idea that if a function is an eigenfunction, any multiple of it is also going to be an eigenfunction, meaning it satisfies the differential equation and the boundary conditions. Okay, so now we can square both sides. So we can square both sides. And the reason we need this is because the squaring function is a monotonically increasing function if we know that x is positive. Or the squaring function is monotonic for positive arguments. Meaning if a is less than b and a and b are both positive, then a squared is less than b squared. But like if a is negative, minus 3 is less than 1, but minus 3 is 9, and that is not less than 1, which is 1 squared. Okay. We can square both sides to get this squared, whoops, is less than the integral 0 to 1 of phi prime squared. In other words, this thing here, this is less than 0. And now what this means, 1 over gamma, if I take the minus sign and distribute it into the inside there, let me just do it like this. If I take the minus sign and I distribute it here, in other words, this, I'm going to have a minus sign and then a plus sign. So this is less than 0. If I multiply it by minus 1, this is going to be greater than 0. Actually, I've only proven that it's less than or equal to 0. Okay. So then what do we have? So, let me do it like this. Okay, so what do we have? We've got the thing that we started with, this. This is equal to this. Okay. Actually, I need to have it. I need to know this. Okay, so this is greater than 0. Okay, so these are equal to each other. So, all right, okay. The quantity on the left is positive. Okay, because if phi is identically equal to 0, then, so the only way the integral of phi squared could be 0 is if phi is identically equal to 0. That's not allowed, because that would be the 0 eigenfunction, which we don't care about. So the quantity on the left is positive, and the quantity in the parentheses on the right, the quantity in the parentheses on the right is non-negative. Okay, now if gamma is not equal to 0, so we're going to assume for a moment that gamma is not equal to 0. If gamma is not equal to 0, the right-hand side is non-negative. Actually, sorry, this right here should be less than or equal to. So let me just be a little careful with how we're working through the logic here. So if we assume, we want to show that gamma is greater than 0. First, assume that gamma does not equal to 0. Okay, so we're going to start that. We're going to see what happens if gamma is equal to 0 in a minute, but let's assume that gamma is not equal to 0. We get to this right here. So the quantity on the left-hand side is positive. This quantity is non-negative. Well, this is non-negative. In other words, it's greater than or equal to 0. It can't be equal to 0. Otherwise, if it's equal to 0, this is positive. 1 over gamma is not 0. If this is equal to 0, it means the right-hand side is 0, but the left-hand side is positive. So actually, no, it's positive. And the quantity in the parentheses is positive. It can't be 0 since the right-hand side would be 0, but the left-hand side is positive. Okay. All right. Well, so then the quantity in parentheses is positive. So then gamma has to be greater than 0. Otherwise, the right-hand side would be negative. But the left-hand side is positive, so that wouldn't work. Okay. Now, if gamma equals 0, this is phi of x phi double prime of x is equal to 0, or phi of x is equal to ax plus b, but phi of 0 is equal to 0. So 0 is equal to phi of 0, but phi of 0 is equal to b. So then this is equal to ax. But 0 is equal to phi prime of 1 minus, phi of 1 minus phi prime of 1. Well, what is phi of 1? That's a. And phi prime of 1 is equal, well, phi prime is equal to a, so this is going to be minus a. Okay, so gamma equals 0 is allowed with phi prime of 0. Phi prime of x equals x. And when we think about that, if you come back up to the equation, phi double prime is equal to 0. Phi of 0 is equal to 0, and phi prime of 1 is equal to phi prime of x is equal to 1, and so phi prime, which is 1, minus phi of 1, which is 1, is equal to 0. Okay, so this is just for gamma. So now again, so we've shown, that gamma, which is equal to the square root of lambda plus 9, just equal to lambda plus 9 is greater than 0. Okay. So, greater than or equal to 0. So then the first eigenvalue, okay, so in other words, 0 is an eigenvalue. If in this problem with the gamma, lambda plus 9 would be equal to 0, that is. So the first eigenvalue is minus 9. Now, like I said, on the test, I'm going to tell you something like, you may assume that, lambda plus 9 or something like that, whatever the appropriate thing is greater than or equal to 0. And so basically all of this work right here for this particular style of problem, you wouldn't have to do. Okay, so the first eigenvalue is minus 9. So indeed, if we come up here and we put in lambda is equal to minus 9, this becomes phi double prime 9 phi is equal to minus 9 phi. So phi double prime 9 phi is equal to 9 phi. So phi double prime is equal to 0 with these boundary conditions, and we're going to get phi of x is equal to x. So you see how that works there. Okay, now for lambda plus 9 greater than 0, the general solution is going to be phi of x is equal to a cosine lambda plus 9. And we could keep this with the gamma if we wanted to, but I'm going to go back to this, to what we actually have, to b sine lambda plus 9 x. Okay, the boundary condition, the condition at 0 says that the condition is 0. If we plug in x equals 0, that goes away. So we're just going to left with a. It says that a equals 0. So now it's going to be very, very similar to the problem, to the previous, to the last problem from homework 9. So we're going to have this is equal to this. And then the derivative is going to be equal to b square root of lambda cosine, square root of lambda plus 9, right? Plus cosine square root lambda plus 9 times x. Okay. The BC at x equals 1 says, so we're going to have, whoops, what the heck? Oh man, what am I doing here? Okay, so 0 is equal to phi prime of 1 minus phi of 1. So this is phi prime. So I'm going to divide both sides by b. So I'm going to have this 1 minus phi of 1. This is phi of 1. Of course, there could be a b there and a b there, but we just divide by b. And now, that's a 1. Okay. Or we can write this as an algebraic equation. So it's going to be very similar to before. We're going to add the sign to both sides and divide both sides by cosine. And we're going to get, when I say before, I mean to the fifth problem from homework 9. Lambda plus 9 is equal to tangent square root lambda plus 9. Okay, and if we want to, we can come over here to Desmos. This is for the exponentials. If you want to go to the exponential way to show that the eigenvalues have to be non-negative. So we're going to look at square root x. No. square root of x plus 9. And then we're going to look at tangent of the same. We want to graph those. And then all of these intersection points are going to be, all of these intersection points here are going to be where there's an eigenvalue. Okay, and then, yeah. Notice we also have one at -9 as well, which is going to be the first eigenvalue. Okay, so that is it. This took a little bit longer than I meant to, than I intended it to, just because this first part, proving that the eigenvalues were non-negative, took a little bit longer. Like I said, if there's a problem like this on the exam, I'll tell you something like, you may assume that the eigenvalues are non-negative. Or in this problem, I would say something like, you may assume that lambda is greater than or equal to -9, something like that. So you wouldn't have to do this entire first part. So just to reiterate, this part right here, because this part right here, up until this part, all of this highlighted part would not be something that I would expect you to do on the test for this problem, for this type of problem where I say get an algebraic equation. I would give you some sort of information where you not have to do that. However, it's going to be very similar to what we do here for number 2. Okay, but that's it.